Okay, folks, homework 5 is posted on the website under homework, so you can go grab it from there. One thing I'll hope you noticed, my philosophy, instead of giving you daily homework and that sort of thing, is to give you weekly homework, so you try it. I assigned it on Thursday, you try it over the weekend, and then I'm available after class on Tuesdays to talk about it if you have trouble getting started. And I have office hours on Wednesday. And apparently I have office hours sometimes on Thursday, right before class. So again, they're going to get harder. So don't wait until Tuesday or Wednesday to start on them, because they're going to get longer, and you think these are thick as it is, they're going to get thicker when we get into three-dimensional stuff and solving problems. So that's the idea behind it. So don't let yourself get behind and have to not be able to solve stuff. We will have a quiz on Tuesday on moments and couples and that sort of thing. So just study up on that. You've done the homework and stuff like that, so you should know what you're doing. Any questions? Okay, we'll get going. We're going to finish up our Chapter 3 work with this continuation of looking at the reduction of force systems. We're going to take all these forces and reduce them down to single forces and single moments. And where we're going with this is when we reduce this is then going to be able to, when we get into Chapter 4, start solving equilibrium problems. This is our step towards going to equilibrium, is taking these multiple forces and basically combining them into a single moment and a single force. And of course, when we get to equilibrium, we're going to set those equal to 0, which then helps us solve for unknowns. Okay, so this single force, single moment is basically considered a resultant. Lots of words there, but basically the statement kind of will describe it in pictures here next. But basically, the resultant is the simplest force system that we can put together from an original force system, a whole bunch of forces and moments and couples all over the place there, without changing the effects of the rigid body. So again, we'll start off with our engineering baked potato that we always like to look at. And what we're going to have is a set of forces and couples acting on this system. So there may be cables attached, there may be other things attached to the system. And the key thing is then we've got these springs down here, and they're going to have some sort of force in them to keep that thing from rolling off into space. what all those words basically then said is that we're going to be able to take all of those, resolve them into a single resultant moment and a single resultant force, with the key property that it doesn't change those spring forces. Whatever's going on the outside of that particular rigid body there is not changing. So this force system is producing the same forces in these springs as this force system is. So what we're going to see is just similar to what we did with 2 dimensions there. We're going to have a set of forces. So we're going to have a set of forces, and what we're going to want to do is move them to some point. In this particular case, we're going to choose point O. Now, one thing we'll note is that these forces are not concurrent, right? They don't all go through the same point. Each one of them in pairs will individually intersect somewhere, but based upon the fact there's 3 forces there, they're not going through the same point. They're not going through that O. So anytime we move a force, we're going to create a couple. So the forces will move together very easily, but then we also have to keep track of the fact that so let's consider what we're going to do to F1. Okay, so what I'm going to do to F1 is I'm going to take that F1, I'm going to take a parallel line of action. So parallel lines of action there. And I'm going to put a positive F1 and that negative F1 again. So it's not doing anything to the point. Nothing's changed there. It's equal to 0. There's no moment caused. But we'll recognize the fact that by moving that force over there like that, I've got this thing called the couple. Equal, opposite, but not in the same line. So they're going to cause just pure twist. And then the way we're going to do that is use our moment equation. We're going to use that cross product approach there. So we're going to take that R, find some point that we can identify in that line of action of that force 1. And we know basically what that gives us is that perpendicular distance, because remember, the cross product is R times F times the sine of the angle between the two. So we'll continue our little drawing there. So what we've done with this particular situation is we moved F1 over to a parallel line of action, like so. But we also have to have a moment. We're going to create a moment by moving that force out of its line of action and moving it over to point O. I've got drawn off in some angle there because we're going to be doing this in 3D, so basically we'll let the cross product solve that for us, figure out what distance that's going there. What did I call that? R01. And the way we get that is the resultant then is just simply F1. And we talked about that before, that the forces are going to be the same wherever we move them. We're just simply moving them out of the line of action. The one thing that we then create is this extra bit of couple or moment, basically. So what we're going to see then is we're going to move all of these forces. So F1 be in its parallel line of action, F2 and we can see then any point I choose, basically, it's always going to be that combination of those forces. But it also creates the M1 and an M3. So basically the key thing is then what we've done is we've moved everything to a single point. Everything's concurrent now. And when we have that ability to do concurrency then, then we can use our vector algebra. We just simply add them. And if we've got it broken into Cartesian coordinates, x, y, and z, we're just going to sum up all the x components, the y components, and the z components. And noting that we have Vergon's theorem, we can also just express this as so we just see an application there of Vergon's theorem there. We can just sum up all those moments. But then it's just simply summing up those scalar components, the x, y, and z's. So let's talk about what this tells us. Again, this might be a point we're designing. You know, we might have a weld there or some sort of connection and that sort of thing. We're probably going to be interested in not looking at individual forces, but the combination. What's the final magnitude of the whole force there of that resultant force? What do I have to design against? So it's just simply our Pythagorean theorem. That's why we like the Cartesian system. So we just use that. Oh, one thing to note too is notice that I didn't put a 0 here at the R. Any clue why I would do that?
Because it wasn't on a variable so it have to distinguish it.
Well, we don't need to distinguish it. R is going to be the same anywhere. That's the key thing. So R, wherever I pick the point, is always just simply going to be the sum of the forces. M is very important, and I have to put the subscript there because I have to identify the location. I take moments at different points and stuff like that. I have to be careful because it'll change. Moment arms will change and that sort of thing. Okay, so magnitudes. Same sort of thing that we talked about. 3 dimensions, pretty straightforward. Just add that extra component. So, and we can do the same sort of thing if we need to calculate the angles, the cosines. Very straightforward. We just simply take the component in the x direction in this particular case over the magnitude of the whole thing there, take the inverse cosine of that, and we can calculate that angle. I've said this, but basically we'll write it down. The R is going to be the same everywhere, direction and magnitude. Now again, going back, moment's going to be dependent upon where we choose it. And then the force systems, the original force system and the external, the resultant force system are same on those external effects. So again, if this is being held by a set of springs, the forces in the springs won't be any different from one system to the other system. Now, some of our force systems are just so cool that they're special. We got these special force systems that we need to talk about. And these are going to become important when we look at equilibrium. And when we get into equilibrium, we're going to see the issues of basically having less equations available to us. But it's good to talk about them now, because it also helps you in terms of solving them. Concurrent forces. This is something you've already seen, particles. All the forces are going through a single point. Okay, so a hanging ball is a situation. So we got a couple of strings holding this up, and then the weight of the ball and whatever is wanting to pull it down towards the ground there. Now, if we extend those lines of action, what we'll see is that they intersect at a single point. What we're going to find then is that it's equivalent to basically summing up the forces. But the one thing that's missing is the fact that there's no moment there now. And when we think about it, we're not really moving any of those forces out of a line of action, right? If we take and look at it at this particular point, they all go through the same point there. So all of those forces are like we had with particle equilibrium there and that sort of thing. They go through the same point. We can just simply add them together. So there's no moment in a situation here where we have concurrent forces. Another set of forces are what we call coplanar forces, and we just kind of talked a little bit about that, where all of the forces exist on a plane. Say, for example, the plane of this board here. But the key thing is then they're not, I'll make it look a little more, they're not concurrent. So when we consider looking at their lines of action, the individual ones will intersect somewhere, but basically we'll have this situation there where there's going to be some that they don't intersect through the same point. So what we get out of that situation, again, is just what we kind of talked about. We've got forces now that we're going to have to move to some point. We've got our point O here. And when I move them to that point, I'm going to have to take them out of their plane, or out of their lines of action, essentially, not out of their plane. We'll keep them in their plane. When we take them out of their plane, then, what we're going to end up with is, again, just like we did, we're going to move them all to that point there so we can sum up those forces, come up with a resultant. And what we're going to find is then the moment is going to be perpendicular. If all these forces are in this plane here, remember in terms of if we had a force, going back here, if we have a force in this plane, well then to measure my distance, an r value, to that particular line of action, well I'm going to do that in the same plane. So my r is going to be in this plane, my f is going to be in this plane. So what I'm going to get is a moment then that's going to twist about an axis that's perpendicular to the board there, or in that z direction, for each one of those. So what we find then is we have a rather unique system there where our r, And I probably should put up a coordinate system. So Z is supposed to be coming out of the board there. That's my poor attempt at doing that. But what we're going to find then is R will always be in that xy plane. If all of my forces exist in that, it's only going to have x and y components. R has to have x and y components. When I do my calculation for moment, I find that all of my moments then, since my moment arms exist in that same plane there, that everything is going to be in the z direction. All of my moments are going to be in the z direction. Question?
Is R hat in the xz plane, or is it the xy plane?
This one?
Yeah.
R is in this plane.
So is that x or z or y?
Well, it'll be, that's OK. We can do that. Let's put that. So it'll be some sort of xy components, if you want to put it that way. But the key thing is that my moment now will be perpendicular to that. It'll be in the z direction. Did I answer your question?
Coming out of S then?
Yeah.
Oh, okay.
Yeah. That's, again, like my poor attempt there. I have to go three-dimensional. We'll get hologram boards here in the near future. But the key thing then is oops. And again, that's my shorthand for perpendicular there. The moment for this particular system, when I move all of these forces to point O, the moment is going to be perpendicular to R. So my R is going to exist somewhere in this xy plane here. My moment's going to be existing in this z direction here. So no matter where my R is pointing to, my moment will be perpendicular to that. And that gives us some advantages when we do some other calculations here. And then this is what the author notes is called a perpendicular system. And again, that has some advantages when we calculate resultants, but it'll also be useful when we get into equilibrium. We're going to have a different type, well, we're going to have less set of equations available to us. The other special system is the parallel forces. This one's better. One of the best examples I can think of in terms of a parallel set of forces is thinking of a table. So all of those forces, when you think of a table, a four-legged table, not a two-legged table there, but a four-legged table there, we've got weights on it. Well, the legs of the table are pushing up basically to keep that in equilibrium and keep things from falling through. So they're out in space. We can think of the table this way, and we've got legs over here, and we've got some legs on the board there, and that sort of thing. So we're using all three-dimensional space there to look at this particular system. But when we consider what's going on with this resultant, well, when you think about it, each one of these forces are only going to have something in the j direction or in that y direction, right? So they'll only have components in j. When I add them together, I'm going to move them to that point O. But in terms of adding the forces together, they're still going to have that same direction. But what I'm going to find then is my m naught then falls in the plane of the table there. Okay, so when I consider my r, if I've got an r that has a component in the z or the x direction there, I better start thinking about that, because if these only have components in the y direction, then my r should only have components in that direction. But the nice thing then is m naught what I'm saying then is then, since my forces are all in the y direction, that my m naught will only have components in the x and y direction. There won't have, or z. Oh. Somebody's awake. Thank you. So it's only going to have components in that x and z, which gives us that property again, where it's perpendicular to that r, or it's perpendicular to the resultant force, and we'll have another perpendicular system. So as engineers, you want to be able to start looking at those sets of forces and get the feel for, okay, am I in dealing with one of these special situations? Again, when you get into these special situations, you find yourself having the ability to solve them much faster. Instead, you can use the general approach, but you can find out that basically you can solve it much quicker if you understand what sort of force system you're dealing with. So in general, force systems won't necessarily be perpendicular. But if they are, we could do the same thing that we did with the two-dimensional systems there. Remember when we were looking for that single force? Where we had this equivalent system where we could create this sort of thing. And then what we want to be able to do is then take this and move this resultant force to some point on this xy plane here, or xz plane, that gives me the equivalent sort of spring behavior, or the equivalent external effects that this system does. Question?
I was going to ask if the moment in this situation would be zero, like unless the chair is like spinning or something.
Well, you're going to equilibrium. That's where we're going to go in the chapter 4. So we start that next week. But you're going in the right direction. That's where we're going. We're kind of assembling all of this now to be able to see how we can set up equilibrium equations for rigid bodies. So in this particular case, no, it'll be a resultant. But if it's in equilibrium, yeah, r and m will be equal to 0 in the long run. So we're going that direction. But right now, your homework is going to be solving basically resultants and moments, resultant moments. But again, we have that situation like we did with the 2D, where we can move that single force and get the same moment that O would see. Right now, O is seeing a couple here and a force. We're going to be able to move that force to some point over here that if I'm holding it at point O there, basically, it's going to say that have that same effect. It's going to have the same twist, and it's going to have the same R. So that's where we're going with that. What we'll see and it'll be applied to those perpendicular systems. So it'll be the coplanar and the parallel systems. So we'll have a situation here where we got a moment and a force going in that particular direction there, but they're perpendicular. And recall this principle of moments, which basically says in this particular case, it'll be RD. But remember, it was F, the force times a perpendicular distance there. So what we're going to do is set up an equivalent system by simply moving that force basically away from O to create the same sort of twist that my point O is seeing right now. Okay, the key thing is again, like we saw before, R is the same everywhere. So what I'm doing is just simply moving R out of its line of action, or moving it away from point O here to create the same twist that point O is seeing when I assembled all those forces together. The distance d then is that perpendicular distance to the line of action. Oh, is that screen in your way? Does that make it better? And what we've done is just simply moving R, we're shifting it to a parallel line of action. That's all basically we do with this particular approach. And the way we'll do that is talk about how we move a force couple system from one point to another point. Okay, so I've got a couple of points, and say, for example, there was a whole bunch of forces, and I've gone through my calculations, and I came up with a resultant force. And when I moved all of those moments out of its lines of action, we ended up with a moment, or a couple, moment of a couple, basically, at this point A. And what I'm interested in doing is then moving that same system, again, making sure that the external effects there, if I had springs out here, they aren't changing. Okay, so my R isn't going to change, right? Basically, it's just the same R everywhere. But again, now what I'm doing is the same thing I've done with a single force, is I'm taking that force and I'm moving it out of its line of action. So I'm going to end up having another moment or a couple there, but it's going to be a different couple. It's going to be M at B. So again, R is the same everywhere. And what I'm going to do is just simply what I've done before there. I'm going to simply take my moment at B, and I'm going to take moment at A, and I'm going to bring it along. I'm just going to simply add that. So that's that, if you recall correctly, that's why we call this a free vector. Because once I have that vector there, then basically I can just move it to another point. When I'm moving it to another point, I just simply bring it along. We've done some homework along that in terms of 2D. And the only other trick then is then I need to move this force out of its line of action. So I'm moving the resultant out of its line of action. So I need a position vector that describes my distance from B to line of action, generally A in this particular case, and then times my R. Oops. Jeez. I haven't had enough coffee. The key thing here, though, too, is just be careful, because it'll get you with signs and stuff. The magnitude won't be different. But again, what we're doing is we're moving it to B. So my position vector needs to be R from B to A. So when I do my calculations, it'll be x of A minus x of B, y of A minus y of B, z of A minus z of B. So it's going to be the reverse the way we've been thinking about it. But again, it's saying I'm taking that's my position from where I want to get my new moment, and I'm just simply moving this resultant out of its line of action. Okay, so recall what we did in terms of moving that to a single force. So I'm wanting to reduce this. Maybe we'll put that as. This is a little aside here. This is basically how we move from one point to another. We change and take our moment and our resultant force and move it to another point. Now, where we were going with that is we're trying to find a place on this body where there's a single R. And this only works for perpendicular systems. So our goal is to find that place then where that B is now going to be equal to 0. So I don't want an MB anymore. And I can take this same equation here. What I'm going to do is simply plug in a 0 there. And what I can do then is since I've put a 0 here, and again, this is a cross product, so there'll be 3 scalar equations when we get done with this, I can put 3 unknowns in here and solve for this location now, because I've decided that I'm going to choose a point where my moment at point B goes to 0. So I'm looking for that place where there's just a single resultant force. And the way I do it is I set my point B equal to 0, and then I can solve for, like we did in equilibrium, basically some unknowns there. In this particular case, the unknowns are just simply going to be this r vector, this position vector. So that will then, once I solve for that, that will give me the distance from A to B in terms of x, y, and z components. Let's put this up higher. Question? Comment? Somebody want to lecture instead? Oh, there is a question. Sorry.
When you moved the force and then created a moment vector instead of, or no, when you changed the moment vector into the force moved at distance, is that the d vector and the m vector are going to be in different planes or corresponding different axes?
Well, we're talking about a perpendicular system here. So it says my forces are in some sort of a plane or parallel direction. My moment is always going to be then perpendicular to that. So remember in 2D, it was real easy because all I had to do was figure out, OK, where can I move that single force to? Because the moment, I can use that principle of moments, FD equal m. Calculate d, that gives me my perpendicular distance. This is going now into 3D, which is basically the same concept. It can only work in perpendicular systems, though. Does that answer your question, or am I getting close?
You already erased it, but I was looking at the pictures that you wrote were equal to above each other, below each other.
Mm-hmm.
Because like it looked like kind of like D and M were pointing like in the same direction in both pictures, but I was wondering if they're actually like in different axes, but just because it's drawn on 2D board.
It's 2D, yeah. Well, let's talk about that after class. We'll straighten that up. Anyone else have questions, though? Did I lose people on that particular point? So what we're doing is we're just simply finding the place where this force, we can create an equivalent force system now with just a single force. Now, an example of doing this sort of thing is think of a mobile. You've got all sorts of little weights, and some of you might have fish when you were little kids, or little teddy bears, or something like that. There's a single point in terms of that wire. You're going to have one wire holding all of those up. That's what we're talking about in terms of this single resultant here. We're trying to find the location then. Where am I going to put that string so when my mobile hangs, all the little fishies are out there displayed appropriately, as opposed to all piled up in a long line or something like that. So that's where we're going with this single force type system. And it's something you actually do a calculation of in terms of finding things. You might be designing mobiles in your future as engineers or something like that. But we might be needing, we might need to find a location for single forces and that sort of thing in terms of some of the designs you do in, I'm trying to think of crash barriers and stuff like that. So there are issues where you actually want to start looking at that sort of thing. And that's where we're going with this, is just simply a 3D application of that. So when we expand that, we just simply lay out our determinant like so, which then says we can set it up as if we look at one individual equation there, we're going to bring the terms in from max, and then we're going to look at the x terms there. It'll be the y times the rz, and then z times the ry minus the next equation. It's just simply the y. So we need to make sure we bring in the y component from here, do our calculation here in terms of our unknown components, x and z. And if we just wanted to lay them out in terms of not solving that or laying it out in terms of the determinant, that's your three equations. We have our three unknowns, y, z, and x, three equations. So do substitution or use some sort of a matrix solver. So then that gives us the ability to take in these perpendicular systems the ability to find out where a single force would be applied to give me the same external effects that the multiple forces or the force couple that I calculate end up creating on the outside or the external effects there. We'll be ready to design mobiles when we get done with this class here. Now, that's perpendicular systems. We also have to consider non-perpendicular systems. And those are our non-special systems. That's basically our general systems. What we'll find in these particular cases is I'll have a resultant and then I'll have a moment that I calculated at that particular point. So I've taken all those forces and brought them together, taken all those forces out of their line of action, moved them over to A, did my cross products, and I came up with this now simple system, which is a force couple system. But in terms of reducing this one, because it's not perpendicular, I can't go to just a single force. And the reason is since it's not perpendicular to that, basically, what we're going to find is that and I'll use your author's convention. It uses M1 and M2 for whatever reason. But what we're going to find is that a portion of that couple is going to be parallel to the force R. It's going to have a direction parallel to the force R, and then there's going to be a portion that I can create perpendicular. So I can take some advantage of the perpendicular system there. So what I can do is then I can decompose this moment into something that's perpendicular and something that's parallel to this R vector, which is just simply a sum of my forces. And the way I do that is I can take MA and I can multiply it times the unit vector in the direction of R. And I can use my dot product. Remember, my dot product was a way of projecting something onto something else, right? So I can create this unit vector in the direction of R times that. Now that gives me a scalar. And recall then I can take that scalar and multiply it times that unit vector again. And basically what I get is a description of a moment, the portion of that moment, that is now parallel to the direction of r. And the way I get that unit vector is like I do before. I just basically calculate the magnitude. I have r already calculated in terms of x and y and z components when I get to this point. I simply just calculate the magnitude, divide by that, and I get a unit vector. Question?
So the amplitude is just the y component of the MA, that's right? It's just the x.
If you want to think about, if you want to think about r in the x direction, then it's going to be the y. Yeah. So think about that's a good way of thinking about it. Keeps it perpendicular. But we're going to be able to then do with the perpendicular portion like we did before here. But what we're going to find is that there's this parallel portion that we can't deal with. And then this perpendicular component, if I want it, is just simply vector algebra. I just take the x terms, subtract the m1 pieces off, y2 pieces. Sorry, am I in the way here? So that's my perpendicular component of the moment there. I shouldn't have gotten rid of that. And what we can do with that is create this thing called a wrench resultant. And what we'll find then is this is the smallest reduction we can do for that. And I think I'll draw my picture up here. This is the same picture you have, but just so we can talk about it. Okay, so what we're going to find then is that we can decompose it to this moment, or this couple basically in R that are in the same line of action. And you actually see a physical example of this when you consider what you do with a screwdriver. You're putting force on it and you're twisting. So that's your R and your M basically in that same direction there. So you end up with a screwdriver effect there. That's part of our wrench resultant. And the other part is then we can get rid of the M2, that perpendicular component, by setting it equal to 0. And then moving it with an x, y, and z with a position vector again, like we did with the R, the A, and the B.
Is it in 0 or 2?
That's a 2, yeah. I cross my z's, so you can tell when I do a z, I cross the z's and 7s. So what we're doing then is we got this point A here, and I'm going to want to find a point B. Let's Let's see. Go the other way here. Again, just like we did before there, the only thing different about this is I'm moving my R, but I'm going to have to carry along M1, that piece that's parallel to R.
What's this B over here? Is that something else?
No, same B. So these are equivalent systems. So I'm, again, we might think of these as bodies, some sort of a body. And what I'm going to do is simply move that. And I'm going to move that because I'm moving my R, I'm going to have to do a calculation there. I'm going to need to find this distance between the two. But when I reduce it, I can't reduce it to a single R now. It's going to be a single R and a piece of the moment that's basically in that parallel line of action. So it's not a whole lot different, except that I've got this little twist guy, the screwdriver portion coming along there. So what we're doing is, again, creating the same external effects. There's springs or something holding this. We have a system like this. I'm at A. If I hold it at A there, I want to have the same sort of effect that A is seeing here on the body as if I were holding A here. I'm going to get the same sort of effect by moving this R and this M here and essentially getting rid of the M2, that perpendicular portion. Okay, we just talked about this equation. We talked about this equation just a few seconds ago there, that sideline. What we're going to do now, and remember when we were doing a perpendicular systems, we just set MB equal to 0, right? And then solve for unknown x, y, and z components of our R. We can do the same thing now, except that MB can't be equal to 0. I have this piece that keeps coming along with me. So I can find, when I move it to that particular point, I can't set that equal to 0, but I know the M1. If I can calculate M1, and I can do that with the dot product, then basically what I'm going to set this side of the equation not equal to 0, but equal to something. And it's going to be equal to the something that's parallel, the portion of the moment or couple there that's parallel to that line of action of the resultant force. Now, your author does it a little bit different. I did it this way because it makes a whole lot more sense to me. But your author, for some reason, decided that he wants to set R equal to 8 from A to B, which just note is simply the reverse of what I just described there. So it's going to be a minus sign. And the way he lays it out, just slightly different, but again, what you see is it's just simply an inverse. We switch signs there and move it to the other side of the equation. So if I switch that to RAB, basically that minus sign, it'll bring it over here, and it's equal to MA. So just so you don't get too confused, your author switches it and describes it in a different sense. But again, I think this one makes more sense based upon the fact that we talked about how to move things from A to B. So let's try this. We did this problem on Tuesday where we ended up having this little rectangular piece there, and at point A, and we had the B and A, but we ended up moving our 60 at 50 degrees. And this is pound inches, 60 pounds. And actually, that should be in a my green is going. OK, so recall we went through this problem here where we ended up with these components of P. So we took all of those forces on that problem, and we ended up with a force couple system now at that corner. Now, since we were so smart, we knew that we wanted to find basically the intersection of this single force. What we want to find is an intersection now of this force R. We want to move it down to here and find out where I can have an equivalent system. And maybe it'd be best to draw that as an equivalent system. So what we did in that particular day is we came up with an equivalent system there where we just simply move that R there. And what I'm going to do is show you basically how we can do that. So that point, I guess, down here that we're looking for is D. And we did that with just principal moments and knowing what a perpendicular distance is. But basically, we can set it up like so, and then set up our cross product So again, my unit is up there. And forces are down there. And what I'm going to do now is, since I want to find this along the y-axis there, what I'm going to do is put in an unknown y. I don't want an unknown x or z because I'm trying to find this intersection along the y-axis there. So what I can do is set up my equation like so. And then in terms of looking at terms here, that goes to 0, that'll go to 0. The j's have two zeros. The only one there will be the 38.57 times y. And that equals 0. So I'm trying to move that to that point where MD, there's no couple left. So it's 0. I'm bringing that free vector along, the 149, And then I'm going through a calculation here, solving for an unknown y. Solve for the y.
What hat is that?
Question?
What hat is that? Or what dimension is the 3?
K?
That one hat.
Oh.
Thank you.
Sorry, K. I missed the K there. I forgot the K.
Thank you.
Okay, so, and it makes sense. It's a perpendicular system, so all of the moments are going to be in that same direction. So y then will simply be 149 over the 38.57. And then depending on where you're measuring from, D or A, it's going to be positive because I've got it set up as RD to A. But if I'm looking at, if I'm at A, then it'll be just the opposite of that. It'll be a minus sign. Okay, we'll look at a little more we'll get started on this. If we don't get finished, I'll post it on the web. But we'll look at a little more complicated three-dimensional type problem. And this is in your handout there, so if you don't have a handout, go grab it real quick. Are there any more in the back?
Yeah, there is.
Why don't you pass them up forward there? Thanks. Okay, so we have a situation where we have a set of forces. We got this particular weird-looking bar there, but there's a set of forces acting all over the place. And what we're going to be asked for is to basically create an equivalent system to all these forces at point A. Not horribly difficult. So the first thing we're going to need to do then is resolve our forces into components. And in this particular case, it's real easy. So basically, again, we want to get everything into x, y, and z. So if we got a three-dimensional thing, we might have to use a point-to-point thing where we do the 2 points and come up with a unit direction or angles and that sort of thing. But this particular case is pretty simple. But we have to pay attention to directions. So the forces at B then are the two I can basically add together there, because one is going to be in the minus x direction there, minus 300. And then the 50 will be in a minus y direction there and acting down. I don't know what happened to C, but C doesn't exist in this problem. So what we'll see then is the D is a minus 250 in the k direction. And our E is going to be a minus 120 in the I direction, and all of them are in newtons. And the nice thing about that in terms of calculating our resultant force is just simply going to be simply adding those pieces up. And that'll be the resultant everywhere. So whether I wanted it at B, Q, Z, whatever, that's my resultant force. Now, to calculate the moment at A, what I'm going to need to do then is take all of those forces and move them out of their line of action. I'm going to be moving them out of their line of action, so what I'm going to need to do is establish position vectors. So I need to go from R to each of those particular points there. A to B. And this will be in millimeters. And then when I go to D, I'm going to go the same direction. I'm going to go out 200, and then I'm going to go an additional 160 in the Z direction there, or K. And then we just keep going. And again, those are all in millimeters. And then finally, to calculate the moment at A, again, we'll use Vergon's theorem. I'm glad I'm so entertaining. At least somebody's happy about my calculations there. You guys have been so busy writing things. So basically, all we're going to do is just simply sum up all those pieces there. We'll lay out rather quickly what they look like. Let's see. Can I set it up with a moment? First piece will look like that. So R is just simply I crossed into I, which is 0, and then I crossed into J, which will give me a K component. The other one where you extend our reach out there to D, so it'll have two components. It'll be I crossed into K, and then K crossed into K, which is equal to 0. And then our final components like that. And I didn't do the determinant this time just to show you that if you're comfortable just keeping track of I cross J and whether that's negative K or positive K and that sort of thing, sometimes it's just simpler to lay it out like this too. What I will do is post the rest of the solution on the web tonight and let you guys play with it. But that should give you enough to get your homework done and stuff. There is a quiz then on Tuesday, so be prepared.